So the in the calculations, or we can say it is the mechanics of this the shear test. Okay, so from these observations, now we are plotting a shear strain and shear stress. In the observation table, we are plotting these shear stresses values, okay, versus this shear strain. Basically it is a stress strain for a shear stress. Okay, now when my normal stress is 0.5 in the first table, okay, this table is repeated for the second sample, double the normal stress, subjective double normal stress 1, and then third sample again the double, that is 2 kg per cm square. Okay, for a particularly dense soil like a dense sand and or a poor consolidated clay, you get a peak in a stress strain curve. Okay, and then it is decreasing. You get a peak value and then decreasing. Okay, so you have a two shear stress. It is a maximum shear stress, we call it as a peak stress or tau max, and then when it decreases and then it becomes constant, we can say critical or ultimate shear stress. So we have two values for each the graph. Okay, now you see here when the normal stress increases 0.5 to 1, okay, the peak value increases. It is just because I discussed earlier about a simple example like an empty truck and the loaded truck. For empty truck, the driver requires to press the accelerator slowly, so it required a less stress, shear stress, to overcome the movement. As if it is a loaded, normal stress increases, the peak value increases also. Okay, so from this graph, the result of this graph are plotted here. What are these normal stresses? For example, let us say normal stress is say 0.5, 1, 2. This is an example. Okay, you can have any selected value. How we select it, that it also represent in situ condition or site condition, that suppose the sample was extracted, suppose in the undisturbed sample extracted at say 2 meter, and density is suppose 18 kilonewton per meter cube. So 18 into 2, that is 36. So close to say 0.4 or 0.4 kg per cm square. Okay, so your third value should be a 0.4. Sorry, it means 4 kg per cm square. Okay, or near to that, and then earlier you can reduce it to the half. This is the basic concept about selecting the normal stress. Okay, if that background is not known, then you can simply place a soft soil 0.2 you can start, and then steep soil you can start with 0.5, 1, 2, like this. So for a given normal stresses, find out these peak values, peak shear stresses. Also we can record a ultimate shear stress, that is a tau at failure, because this is at the failure and this is at the peak. Then you can plot a next, after stress strain curve, you can plot a Coulomb's curve or Morse Coulomb curve. So we plot a normal stress and the shear stress on y-axis, normal stress on x-axis. Okay, then this from the table, okay, normal stress suppose 0.5, 1, 2, and these three values 0.5, 1, 2, and suppose the peak values. This may be a graph for a peak value, this may be graph for an ultimate value. Either you can plot both or you can plot any one. Normally peak stress is also required, so you get a 3 point. They are not a linear, because it's not it is a natural soil. Okay, all particles not necessarily same particle, so friction developed between each particle is different, so you get slightly non-linear, non-collinear, but not much variation, very close. Then you can draw a best fit line and you can extend. Keep these both scales same, it intersect here. Okay, So measure this is called as a cohesion. C, you can measure cohesion C. It has unit of say kilonewton per meter square or kg per centimeter square. Cohesion. Measure the angle directly. If the scales are same, you get a phi, angle of internal friction. And this is how you get the result C and phi. Using this, you can find out for side condition what is the normal stress. If you know at side condition, you can find out the shear strength of the test. Doesn't give directly shear strength, it gives the shear parameter in different drainage condition. Okay, this is in undrained condition, is called as CU. This is in a CU condition, consolidated undrained, it is called as CCU. Or if it is in drain condition, then it is called as CCD, like this. Additional information also we get it. Okay, we installed the two dial gauge. One is for vertical displacement, one is for horizontal displacement. Okay, you get the either any one of the graph. When it is a loose sand, what happens? In a loose sand, the volume goes on decreasing. Particle are moving together, decreasing the void ratio. So you get a curve like this. In a dense sand, it is already less void ratio. So further it can't move, so it will try to expand. Okay. So initially, after certain horizontal or negative value, this expands. So this is called as a dilation curve. Okay. So this dilation, what is important? Dilation means it is a here expansion. Okay. And that is how you can find out. So slope of any one of the graph you get it is called as a dilation angle, and which is very important when you do some modeling. That time on this value is very important. Okay. Now next we move. The most important part again is the principal plane and principal stresses. Now the test is over. We have plotted this failure envelope. We got C and phi values, but here more circles are not used. Okay, it's not required because on the element we apply normal stress and shear stress. So there is ABCD, suppose surface boundary, then ABCD are not the principal planes because tau is not 0. So therefore you can draw the more circle, but indirectly you can find, or after the test you can find out the principal stresses. So for that, any given point on the failure plane, suppose F is given any failure point, its coordinates are sigma and tau. Mark this. Okay, then draw a perpendicular, that is FC. So FC is a center, FC as a radius. Draw a circle. Circle cuts at A. OA gives me sigma 1. It cuts B. OB gives me sigma 3. Convert back to the scale. Okay, this is how I get sigma 1, sigma 3. Now here the procedure is slightly reverse as we discussed the Mohr circle earlier, because here failure plane, the point of failure is already known, the pole is not. Earlier, how we do? From A, we draw line parallel to the plane. Okay, AB. Okay, we get A. It intersects circle, we get a pole. Then we draw the second. But here pole is not known. So from